So, we are into our lecture on systems approach. Now, because systems approach is an integral component of PHM SA, so we will be having two presentations which will be introducing what we mean by systems approach. Okay. So, here we will see that in systems approach, we have first level is a probabilistic risk assessment model of the plant. What this model says, it integrates all the components, their performance. The component could be safety system, it could be process system. Process systems appear in inventory, okay, and safety system also form header of the inventory. We will see what is the inventory and what is the fault tree. And safety systems are analyzed using essentially using the fault tree approach. And fault tree, inventory together, they in a broader way, they create the probabilistic risk assessment model of the plant. So, this is one level. Okay. Then second level, these two together, they will give us the integrated risk based approach. Now, what is integrated risk based approach? In safety assessment, there are two methods of risk assessment. One is called deterministic, traditional approach, where we design the system for a purpose, and then using factor of safety, redundancy, diversity, okay, and quality assurance program, we say that okay, this system is sufficient and chances of its failures are negligible. Then we integrate with the plant. We say that there is sufficient redundancy is built into the system. So, the failure of a system is less because there is a redundancy built into the system. Okay. And then this particular model is validated for each of the postulated initiating events. Okay. So, if you read even 10-15 pages of probabilistic risk assessment and deterministic safety assessment, otherwise I'll have special one lecture on deterministic safety assessment. So, these are all traditional methods. As I mentioned, factor of safety is at the core of designing a component, and then using the finite element methods and other advanced methods, the components are designed, integrated into the system, and the plant is built. Okay. And finally, during commissioning, they are tested. But probabilistic risk assessment is something when you have design of the plant, a PRA model is created wherein safety system are developed, and then process system failures account for the initiating event. Like let us say for example, loss of upside power is an initiating event in the plant. Okay. And then safety system is emergency captive power diesel generator or battery banks and all the safety systems, how they respond. So, they are characterized in terms of probability, probability of their activation given a demand. Okay. So, so we have an integrated risk based approach. It is called either integrated risk based approach or risk informed. In regulatory parlance, it is called risk informed approach. But when we design a component, we use probabilistic method, and therein it is called risk based approach, because the risk based goals, criteria, methodology, they are implemented okay, for any application. Now, the integrated risk based engineering is a subject that was developed by me, and I have published a book on this. Okay. So, you can see on the internet, or maybe you can see some slides on risk informed, risk based things and all that. So, now the core model is integrated risk based engineering model in our lecture, and using this one application of spin off of risk based approach to operation maintenance. So, it is called risk conscious operations maintenance management system, risk conscious RCOM. I will be using this word RBE, risk based engineering, RCOM, risk conscious operation management. Okay. Now, so with this third layer, we come to our field, that is risk conscious operation management, because management is maintenance management is part of PHM, or PHM is a part of maintenance management. Now, and then we have integrated a system model for implementation on PHM. So this is how we in stages we have evolved. So here in this slide we will discuss these three things, that is probabilistic risk management, risk based engineering, risk conscious operation management. This will be the scope of this lecture. And then the alternate way is there, systems approach. Even PHM, some publication I have seen where they use failure mode effect and criticality analysis. But then FMECA does not give interdependency, common cause failure. They have the component listed, and they identify the failure mode, failure mechanism, and based on that they optimize the PHM program. But it is my belief that you need a probabilistic model to have a identification, prioritization, all those things, and then based on that PHM can be implemented. So this is the alternative. You can see in the literature, it's available in open literature. So let us see. See, that means we are talking about operation and maintenance management. So that means we have to see what is O&M. O&M I am using for operation and maintenance. This is acronym for operation and maintenance, that is O&M. So what is the paramount philosophy? Safety is an overriding factor. What it says? Safety is overriding factor means any decision has to be taken. If you have to choose between plant's operation and safety issues are there, safety issues will be given priority, and safety should not be even seem to be compromised. That is what it means. Okay. And then human interaction. Operation ecosystem is human action intensive, because typically a operation system or complex system is characterized by all the parameters into the control room, and then there will be control panels at the back of it, and then this will be maneuvering the plant operation shutdown things are there. So and plant operates 24/7. Like if you take any of the complex system example I had given, they operate 24/7. System is complex. Interdependencies are inherent part of complex system. One system is depending on other. Their interaction are complex. Their operation is complex. And then management. A couple of agencies are involved. Not one agency. Like there will be one operation agency, there will be another maintenance agency, there will be another service agencies, and there could be even domain specific requirements like physics, chemistry. They all come, and with and of course regulatory. Regulatory is also part of because on perpetual basis plant safety is ensured through an independent body, and of course by the plant itself, and the interaction happens, and then decisions are taken, especially in the area of safety factors which are affecting safety. There is a commitment ensuring delivery, but that safety is a paramount factor. But always there is a commitment to deliver. In a power station, electrical power output is the deliverable. In a chemical plant, chemicals are output. Take the system in a oil industry. It is the discharge of or delivery of oils on time is the so like deliveries are so important, but then safety should not be compromised. And accidents probability should be low because it has got local consequences, organizational consequences, national and international repercussions. So accidents should be rare thing, and that's what the operation consciousness, operation conscious, risk conscious system is there, so that this situation should not be seen in the life of the plant, especially serious accidents. There is an element of randomness, be it performance And we are dealing with randomness. Small variation here and there, whether it is a human factor or whether it is a component failure, component testing, procedures. So all these factors have to be ensured, and that's how the uncertainty characterizes the randomness and that is a core part of probabilistic modeling. Uh, Independent regulatory agency oversees the operation, and plant has to be shut down if the regulatory agency sees any compromise in the plant, and after getting the clearance only plant can be started. This is the last stage. Compliance is a regulatory compliance is a procedure, periodically it is performed, but if required, regulators have power to enforce shutdown of the plant. Typical O&M ecosystem attributes. Like if I take the example of a nuclear industry, the technical specification for operation is the most important document in the plant. So it stipulates limiting condition for operation, okay, and safety rules for operation and maintenance that includes surveillance, outage stipulation is also human factor and forms a approved document by national regulatory body. So this document should be followed in toto, okay, and it should be periodically reviewed and updated depending on the plant modification updates and all that, So periodic reviews. Tech spec define the limits condition for operation that includes limiting safety system setting, periodicity and all. So for different plants, there may be different technical, the name of the document may be different, safety technical specification or some, but these things have to be met, and they should not be violated. If any of the clause of tech spec is compromised or seen to be compromised, the regulators have to be informed and their compliance is required. Plant operation conform to technical solution, and any deviation from the test requires a review of the regulatory body and approval. Traditionally, the surveillance test and maintenance intervals are based on the experience. This is a point of interest for us because all maintenance intervals, because it is a periodic maintenance. Periodic maintenance, time-based maintenance. So these things have to be approved, and PHM is a different angle. So far, I'm not sure whether regulatory bodies have encountered any case on PHM, but the moment it comes and reach that stage, probably this will also become part of the regulatory review. There is an increasing interest in reliability-based test maintenance. Of course, risk-informed approaches are becoming part of the regulation. Okay. So that much advancement is there. That means PRA, and second thing, PRA itself has become part of compliance. That means if a plant is designed, the PRA level 1 reports are required. We will see what is level 1, level 2, level 3 and all. And then O&M event is so root cause investigation and root cause analysis. Small incidents, they keep happening in the plant. So it is better to pay the attention, and these things should be nipped in the bud actually, because if we do not take control of those things, they get aggravated. So incidents should be seen seriously, and for that, if required, root cause analysis is not performed for all the incident, but for low consequence or event which are not having, but then they should not repeat, and there should not be any generic factor in that event. So we have this RCL, root cause analysis. Root cause analysis is in broader sense. It is a procedure which has to be performed to understand the root cause of the failure. Okay. Even if it is a root cause, like human is common to all the stages, conceptual stage, design stage, operation stage, maintenance stages and other stages also. But then what caused the human to fail and all? Is there any institutional lack on that? So this has to be understood. So root cause analysis becomes an integral part of any plant, and it is performed at 3 levels. The elementary one, which does not have much consequences, 6 months or 1 year, less than 6 months, and level 3 has 15. I think this has to be corrected. Level 1 is 15 days to submit a report, and level 2 is 6 months, and this one. So like that we have to take it, say 6 months to 1 year, and then takes 6 months, less than 6 months. This is level 2. So level 3 is generally 5 to 15 days. This should become level 1, level 2, and level 3 should be 6 months to 1 year actually. Okay, this numbering is can be revised actually. Okay, so then other factors, salient feature of the modeling are information and data collection from the incident site, interview with the staff immediately involved in the and where, like if it is round the clock shift, who are the operators manning the area, mechanics. So development of chronological order of events, how the events have happened, mapping the event on PRA model of the plant. So it is called precursor analysis, and try to understand the consequences from there. Availability of RCA matrix, this is the matrix. If the consequences are high, then is level it should be level 3 actually. So all this level number will change from 1 to 3 actually, you know. So like this one here, okay, and high, both are high, so consequences are high. So it should be go to the level 3 category, and these type of events are very rare, not many. Once in 3 years, one event or so something. So, but suppose if this consequences are low and likelihood also is low, then it goes to the category of level 1 and all that. So this has to be seen in that context actually. Okay, so now root cause analysis, then O&M risk conscious safety culture. Safety culture is the normal terminology that is used by IAEA and internationally also, but risk conscious culture is something we are directly talking about the numerical values, okay, and for these attributes there is a quantification, okay. So these are the part of the safety culture, safety assessment model of the plant using deterministic and probabilistic, and now even regulators are insist on both the approaches, the modeling of the plant, training and qualification, safety conscious operation management, surveillance testing culture. So periodic testings are performed, like it is a part of again maintenance. Then a reference human model through training and qualification. Okay, this is something we'll be discussing in details. Reference human model. What are the training levels? Okay, so that human model we'll see in the next slide. Organizational level, safety conscious management, and then safety conscious culture. If any event, there is a 1 in 100 chance of common cause event failure, but if it happens, it is in-depth analysis of the common cause failures have to be done, and the causes, even though plant has many provision for to avoid the common cause failure. I said physical separation, independent power supply, and then elevation, location of the component. There are so many factors, but still common cause failure occupy a important dimension in probabilistic risk assessment. So attention should be paid. Resources, human time allocation and scheduling. So finance, facilities and function. These three factors should be ensured in perpetuity. Proactive approaches. Root cause and precursor analysis. Precursor analysis, when you map an incident on the PRA model of the plant, it is called the precursor analysis. And root cause analysis is first we are having how the failure has occurred and how it could have been avoided, and then for seeing its impact, it is a precursor analysis that is done. Independent safety review by a regulatory body, yes, these are part of risk conscious culture. And then higher plant reliability availability, often disruption and incidents have been found to be the major causes of unavailability and life. So plant availability, which ensures the financial bottom line of the plant, or availability of the plant, and then reliability, that is uninterrupted operation of the plant. Okay, and safety is a paramount overriding factor, we said in previous slide. So Now, of late, new elements have entered. As I mentioned, modeling and role of PRA is now becoming part and parcel of the culture, safety culture. Computerized operator aids. Slowly, information systems are being built into the plant. But operator aid for emergency operation, some plant do talk about it, but computerized aids should form part of the plant operation, because during emergency the stress levels are higher, and cognitive capability to understand and analyze tend to get compromised. So, if it is a computerized procedures are available, one can be rest assured that there is some information advisory system is available. Of course, the final responsibility is with the operator. Support tool and methods for remaining life assessment, it is required, because we should be having clarity, especially on certain selected component, that what is the life, because suppose if some component fails and it takes away 7 to 8 days of availability, then from reliability point of view also remaining useful life is important. But suppose if some component fail and safety is compromised, then in that case we have to have remaining useful life. One can imagine there is a center where you are getting information about the health of the component. At present, we have a control room where status of the component is given, and once the desired status is there, the control room shows all clear. I am just using a very brief description, and the plant is operating smoothly. That is a signal. But suppose if there is an incipient degradation, the technology goes to that level, then it is that the separate desk is required to ensure that component are not entering into the threat zone, or they are not we are not going to plant staff is not going to encounter any failure of the component. If that information is available in advance, then it becomes easier to for the management. Then simulators are becoming part of the control room. Simulator provides a very good ecosystem for training, where training is faster, well understood, because the reason is you can manipulate the systems over there. You can press a switch and see what happens in the system. But just if you read the manual and this thing, then you do learn. But then the process becomes very crisp, and it is accelerated when we are having a plant simulator. In-house labs and R&D for qualification of component. Quality things should only go into the plant, so there should be a quality control lab or R&D lab which always keep working on the advanced areas to make the plant more and more safe, and that's how the safety is not compromised. So, as I mentioned, probabilistic risk assessment is coming out to be, because it is fundamental for risk-based engineering and risk-conscious engineering. So, let us understand what we mean by probabilistic risk assessment. Definition we will see. So, definition is a comprehensive structured approach to identifying potential failure scenarios, constituting a conceptual and mathematical tool for deriving numerical estimates of risk. So, that means it does not remain in qualitative domain. The safety is defined that the damage probability or frequency is 10 to the minus 6, 10 to the minus 5, 10 to the minus 7. So, we can compare with and understand the safety, and when we do any modification, how the safety is improved or risk is reduced, that also can be seen, because it is an integrated model of the plant. Probabilistic risk assessment is an integrated model of the plant. The NRC uses probabilistic assessment to estimate risk by computing real numbers to estimate what can go wrong, how they are likely to happen. So, these are the three questions you have to ask: what can go wrong, how likely to happen, what are the consequences. So, this is how US NRC's model is there for probabilistic risk assessment, fundamental model for PRA. Okay. And then comprehensive, systematic, structured, analytical approach to postulate the potential. And here you can simulate the accident and see how it changes, how the risk changes actually. So, it is a sort of it is normally used as a living tool also, or as a risk monitor type of thing, you can say can be used. Okay. And then objective is to find out, even in normal condition, find out the strength and weakness of the plant, so that our services or our resources can be focused, and attributed to the important risk significant or safety significant component more compared to the one which are not affecting much. So here we have level 1 PRA. In nuclear parlance, core damage frequency is the estimate given here. Inside you get about the plant safety of the plant safety, design and operation and risk based applications. Okay, so these are the insights that are available for design as well as operation, and its applications are many. Like we can say even the technical specification optimization is one of the important. Then development of operator support system is a basically can be done based on the model of the PRA. So like that many tools can be used. Then level 2 should be level 2 PRA, and this is level 2 PRA is again release frequency. Okay, accident has happened and what is the probability of release. Okay, and what is the risk to the in the public domain, level 3 PRA. Okay, and then the plant design, deterministic safety and analysis and operation. So this happens with the design input, operation inputs, and based on that the PRA level 1, level 2, level 3 model is there. Okay, so this is a case for nuclear plant. Okay, so now we say that systems are analyzed. So let us say a power supply system, fault tree for emergency power supply system. Under voltage, there are two buses, and how this can happen if both the buses fail, AND gate is there. This is a fault tree. So AND gate means this and this should happen, then only it will be a power failure. Class 3 means emergency power. Under voltage on bus, and then how this can happen? It can happen because of diesel generator failure, or it can happen because of power supply from other alternate bus. Okay, so like that. See, so from other bus also is not coming. Then we have DG1 circuit breaker failure, CB circuit breaker failure. Their abbreviations can be given actually. So CB is circuit breaker, DG is diesel generator, and common cause failure, diesel generator. So if there is a common cause failure, both the diesel generator will come. If this fault tree can be reduced also, if we operate on the Boolean logic, we can have this fault tree which is a reduced fault tree, and you will find that the components are not repeating. The CCF DG will not repeat here. It will come into one place as a common cause failure, And then we have event tree. So now you analyze this, quantification has been done. Let us say, assume that the failure probability for these components are available, and you got the top estimate of the, then you will plug in into the event tree. And the event tree is loss of offsite power. Loss of emergency diesel generators are required to operate during loss of offsite power. So along with other things, we have estimate of emergency diesel generator, it is 6.5 to 10 to minus 4 or something. Okay, and then based on that you create a output grid for distribution of core damage frequency. Okay, so the minimal cut set that you get if you develop through the Boolean logic will be common cause failure DG, DG1 and DG2. So that means either this component alone, as I mentioned you, common cause failures are very important for any plant. So this is single cut set, single order cut set, and it fails. So the class 3 power will fail. But otherwise for other things, DG1 and DG2 has to fail, CV1 and CV7 and CV2 should fail, DG1 and CV8 should fail, and then CB7 and CB8 should fail. So you can see here, you will see for yourself if you apply the Boolean logic, and you can see these failures actually. And finally, you estimate the core damage frequency. Whatever consequences coming on this side, if you add together, create the summation of this frequency quantified estimates here. Okay, because you have this frequency, so you can get unsafe failure. If you add there, you will get core damage frequency statement. CDF means core damage frequency statement. Overview: a broad approach for implementing risk conscious culture, and then estimation of O&M ecosystem, essential elements of O&M ecosystem that we have discussed. Introduction to PRA, 3 levels of PRA we have discussed: fault tree, event tree, and the measure results that we have shown there. And probably you got an idea what we mean by PRA. Actually, when we do a PRA study, the document could be almost in thousands of pages. But here I have given a simple example, a simplest example to explain to you how PRA models are created and how the core damage event. This term is applicable for nuclear plant only. So the can be is estimated, and this core damage statement is of the order of 10 to the minus 6 to 10 to the minus 5 means very low. Chances of event happening is very low. So, in the line is risk based engineering, next lecture.